Today we're going to talk about nearest neighbor methods as part of our pattern classification course. Nearest neighbor methods are some of the simplest methods of classification and regression, and they will also serve as an entrance to our discussion of supervised methods. We'll continue on discussing different supervised methods like SVMs, decision trees, artificial neural networks, etc. And I think nearest neighbor methods are a good introduction to supervised learning. And they're particularly useful in some domains like computer vision and biometrics. And hopefully we'll see kind of a hands-on example of those when we get there. Okay, so let's first define what supervised learning is. So far what we've seen, we talked a bit about Bayesian decision theory before while we were doing the class in the classroom, and we've kind of gone over the theory of how we decide based on prior probabilities of different states of the world. We'll start calling them classes, and what the prior probabilities were, what the conditional probabilities given the inputs were, and we actually kind of defined supervised learning then. But essentially, after that, we looked at exploring data and unsupervised methods like PCA. Right now, we can actually move on to supervised learning. So in unsupervised methods like PCA, there were no class labels. So now we're going to talk about a new kind of data set where, just like in PCA or other unsupervised methods, you have a set of vectors, each vector being an m-dimensional vector of features for one instance. In this case, we'll subscript the instances with I. So let's say you have n examples in your training set or in your data set. We'll call this the data set or the database, D. And for each instance, you now also have what's called a label. Notice that the instance itself is a vector, whereas the label is generally a single scalar value. So, and we're assuming that each vector m has a dimensionality, each vector x has a dimensionality m. So this could be a two-dimensional problem, 64-dimensional problem like the one we saw with handwriting, etc. So that m is how many elements each x vector has, and n is how many instances you have. And now for each instance you also have a label, somewhat like, for example, in our previous discussion, the salmon and the sea bass were possible labels. So going from the salmon and sea bass example from before, for example, each x vector for each fish could be a vector of its width, height, the lightness of its skin, etc. But now for each instance vector of such measurements, we also have a known label for that thing. So these labels can be of two forms. They could be real numbers or kind of continuous values, like, for example, duration, cost, etc. Or they could be nominal values like either sea bass or salmon. And when it's a nominal value, we typically represent them as integers. So for example, if you have three classes, they could be -1, 0, or 1, or 0, 1, 2, etc. And it depends whether you have -1 or 1 is kind of whether your classes are ordinal as well. Well, so if there's an ordering between classes, something like low risk, high risk, very high risk type of classifications. So the numbers are just placeholders, and they're generally integers for classification. When you're doing regression, they tend to be real numbers. So let's take a look at the difference between classification and regression. So if you're given a data set D with these pairs and kind of pairs of instances and labels for each, essentially the task of supervised learning is finding some mapping, some function that will take a new vector x of kind of new measurements and map it to an estimate label, so an estimated label, and we'll call that y hat, such that this estimate y hat is as close as possible to some true label y. We might not know the true label y, especially if it's a novel example. Let's say we created our mapping, and the creation of this mapping is what we call training, with already existing data that had been labeled before. And then you have to kind of figure out your estimation of y for a new value, a new instance, and that value y, you don't know whether it's true or not, but you can kind of estimate the accuracy of your system as well by looking at the already known x's and their y's, and you're trying to figure out the function, the mapping that does the right thing for as many of the yi's that you do know. And we'll talk more in depth about this when we go to when we talk about model selection and evaluating classifiers, maybe 2 weeks later. And we'll talk about a lot of different ways you can evaluate these things, like holding out part of your training set D and only training with part of it, and then testing with the remaining part, things like cross-validation. We'll also talk about theoretical methods of figuring out whether your method is doing the right thing, with things like minimum description length, etc. But that's another lecture. I'm not going to go into that right now. Just for now, we'll just assume that we know what x is, what the x's are, and what the true labels y are, and we kind of figure out accuracy that way. So, like I said before, if these labels are nominal or ordinal, kind of, and they're finite, generally, so if your y estimates and your y's are part of the class of integers, we tend to call this classification. Or it doesn't have to be integers, it could be any discrete set. We call this classification because now those integers each correspond to some class, like sea bass or salmon. When they're real, so continuous, and this mapping would be called a regression. So now you give a new x, and it gives you some value of x. So, for example, you can give certain attributes of a patient, and it gives you an estimate of, say, the size of an aneurysm, or so on and so forth, in maybe in the future. Okay, so that's regression. For our discussions today, we'll mostly talk about classification because kind of discrete classes and discrete decisions are easier to illustrate things on. Another distinction I want to talk about today is two types of supervised learning. We have model-based supervised learning and instance-based supervised learning. So the difference between these is in a model-based learning method, you take the whole training set D, the data set, and you try to distill it into a simpler and usually parametric model. So what we did before with the salmon and sea bass was something like this. We took the distributions of, for example, the lengths of salmon and the lengths of sea bass, and we found a cut point between those two distributions where you would mostly accurately classify these fish. So that would have been a model-based method. So we found a model, in that case, a decision point, which kind of classified the two different classes from each other. So we kind of reduced the whole data set into one point, so to speak, where you say if it's less than this point, it's sea bass. If it's more than this point, it's salmon. And this is, when you do this, generally the mapping has very few parameters. So you might have a huge number of fish, like, I don't know, a million sea bass and a million salmon in your data set. So N is very large, but you're going down to, let's say, just a decision point on length, which is a single parameter. So you're essentially, number of parameters is very small compared to the number of examples in your training set. So a good example of this is, like we said, decision points or decision stumps, or more generally decision trees, which take this whole set of data and come up with a rather simpler set of decision points, which might have just a few parameters. A lot of artificial neural networks are again model based, because they burn through your data and look at the labels, and based on the loss on those labels, they essentially tune a finite number of weights, usually assumed to be less than the number of weights in a neural network is assumed to be less than the number of instances, and therefore they're kind of both parametric, and they don't keep the whole data, they just keep the reduction. SVMs are a difficult class in this matter. There are both instance-based SVMs and model-based SVMs. Model-based SVMs generally just reduce your whole data set, your points, into maybe a few support vectors. And if the number of support vectors, and if it doesn't mean anything right now, the term support vectors, don't worry, we'll learn about them next week. They can be seen as model-based, whereas especially if they're lazy SVMs, and the number of support vectors is comparable to the number of instances in the training set, you can think of them as instance-based. Same thing with ANNs. There are certain neural networks that can be thought of as instance-based, things like self-organizing maps. So what is instance-based supervised learning? In that case, you don't really distill your data set into a simpler model. You'd keep the whole data set as part of the model. So the whole training set, D, or at least a large subset of it, is part of the learned mapping. So you might potentially have as many parameters in your model as the number of instances there are in your training set. And therefore you can think of these as non-parametric. So this is kind of the model-based versus instance-based. In one way is kind of like the difference of taking a bunch of examples of, say, for example, people's heights, taking the average and finding the standard deviation, and then saying, okay, the people's heights are represented by this, say, Gaussian curve. An instance-based method or a non-parametric method, what you do is you don't do the Gaussian, but you build a histogram of those people's weights. So now you have a bunch of bins, essentially more parameters. In the model base, you just have two parameters, the mean and the standard deviation. So that's kind of an analogy of model-based versus instance-based. And for most instance-based methods, the classification itself is actually now just a form of lookup over the existing training set. And this, we'll see how this works with nearest neighbor methods. Those are probably the epitome of such methods. So there is no really training step. You just dump the data set, the training data set, into memory, and whenever you get a new instance, you look up from the data set the closest instances, the nearest neighbors, so to speak, and then just kind of classify accordingly. So obviously, k nearest neighbors is an example of an instance-based supervised learning method. Like I said, some lazy SVMs can be considered instance-based learning, and certain classes of ANNs can also be considered instance-based learning. So, talk about KNN. or rather nearest neighbor methods. Let's start with a toy example of data, and I'll try to keep this toy example constant as we go. So what we have is a two-dimensional data set. Obviously, each instance X is made up of a vector of two elements, and we call them X1 and X2. So, for example, this point over here would then be just, let's call this the first point. The first item is essentially roughly it's 2 by 2, so it's 2 by 2, right? So this is, as always, X1, and this is X2. I'll try to keep this convention as much as possible. So if you see a subscript, that refers to which dimension of the instance that we're talking about. And if you see a superscript, it kind of represents which instance in the data set we are talking about. Okay. So now basically we take our data set and we kind of put these points into some database or into memory. And now remember our task is, when I get a new X, vector X new, I want to be able to map it to some label. And we can assume that, for example, each one of these existing points have labels. So, for example, these guys, let's say we have two classes, red and blue. These guys could be red, and these guys can be blue. Now the question is, if I have a new point that's over here, is it red or is it blue? So the way to go about this is to kind of take your new point, in this case, let's say this red one is the new point, and find the nearest neighbor to that point. And obviously you can use different distance measures, but if it's Euclidean, essentially you're looking for the smallest circle you can draw that, for example, if I draw this circle around here, there's really nothing inside that circle. I'm trying to find the smallest circle I can draw such that there's one other point in it, and that point would be the nearest neighbor. Like this. And again, notice that this is, when you're using this circle as the kind of neighborhood, you're essentially using Euclidean distance. So we're using, for the green one, this one basically is L2 norm or Euclidean. And what you use as a distance measure, as a distance metric, will affect what essentially what result you get from nearest neighbor. So just to illustrate this point, let's say I have some other point here that's right there. Let's give it a plus to distinguish it. Now, when you think about it, is this point now the nearest neighbor with respect when compared to the original nearest neighbor we found? Well, obviously it's inside the circle. It's part of it's on the kind of it's on a smaller circle centered on the query point, the new point. So normally if you were using L2 norm, this would be the closest point. But let's for now assume that I'm using not L2 norm, but L1 norm. Remember, this is Manhattan distance. So when I have 2 points now, the distance between them for these 2 points, let's make them black. Euclidean distance is just the kind of as the bird flies closest distance to it. Manhattan distance, remember, is you go to the correct coordinate in one axis and then you go to the correct coordinate on the other axis. So you're moving like a taxi cab does in Manhattan. So obviously these two are different. So if I were to map L1 norm onto this space, what would the boundary look like? We know that it looks like a circle if you're talking about L2 norm or Euclidean. Think about for a minute what a boundary would look like if you were using Manhattan distance. So I don't know if I'm going to be able to draw this correctly, but the boundary of the same size with the equivalent boundary for Manhattan distance would be actually this rotated square or diamond, right? So, and when you think about it, this is kind of obvious. So distance of this point to the new point is exactly 1 if this kind of half diagonal of the square is 1. And so is this point, and so is this point, and so is this point. But if you look at this point, and all points on this kind of rotated square have Manhattan distance 1, whereas this point is outside. So when you think about it from the point of view of Manhattan distance, this one is still the winner, because it's within a Manhattan distance of 1 of the center point. So this is the winner for L1 norm, and this one would be the winner for L2, so Euclidean, because it would be kind of closer than 1. So this is just to show you that this distance metric that you use actually will affect what's the nearest neighbor and what's not the nearest neighbor. So how do we find the nearest neighbor? Kind of algorithmically speaking, it's kind of a very straightforward method. So what you do is you take your data set D, made up of these pairs of instances and their labels, and then you actually find the label for a new point. What you do is you initialize index of the nearest neighbor initially to none, and the distance of the nearest neighbor to infinity, because we don't know what the nearest neighbor is. For all we know, it could be infinity if there are no other points, for example. And then for every point already in your data set, you calculate the distance of that point to this new point, and if that's less than the distance of the current distance of the nearest neighbor, which it will be for the first point, obviously, since the first point x1, x superscript 1, will be a finite distance, then you replace that point's index with the index of you replace the index of the nearest neighbor with the index of that point, and you change the distance of the nearest neighbor with the distance of that new point, and you keep doing this for all the points in your training set. So what you're doing is actually classification itself uses the raw data set. There is no explicit training involved. And you keep doing this, and when the for loop is done, essentially what you've done here is a min operation, right? You found the minimum distance of a point to the point you're looking for. So you found the point with the minimum distance to this new point, and then for nearest neighbor, all you do is you return the label of the point you found. So whatever this xi was, actually, I'm sorry, this is not correct. Let's fix this. You don't return yi, you return, let's make it black. You return yi and n. So you return whatever the label is for this nearest neighbor that you found. And that's basically nearest neighbor classification. It's pretty simple. An obvious extension is you can not just take the nearest neighbor, but you can take, for example, the 3 nearest neighbors, or the 4 nearest neighbors, 5 nearest neighbors, etc., and take a look at their labels and decide the label of this new point based on a group of methods instead of one. So not just the nearest neighbor, but the nearest 3 neighbors. And that's where the name k nearest neighbors come from. You decide on a k, and you look at the labels of the k nearest neighbors. Before we talk about k nearest neighbors, though, there's a kind of a small discussion to be had about decision boundaries. So let's say this point, and for now, just ignore all the points other than these two, just for now. So act like these points here do not exist. So in your data set, there's only these 2 points, 1 and 2. And now, if that was the case, if I was using just the nearest neighbor, if I had a new point like this, what would be its class? Would it have the class of this point or that point? Obviously, it's going to have the class of this point because it's closer to this point rather than that point. And the way we decide that mathematically is you build a decision boundary between these points. And you know that on this line are all the points that have exactly the same distance from both A and B. And if your new query point is on that side of the line, it has to be closer to A. If it's on this side of the line, it has to be closer to B. So essentially, this boundary decides what the class of the new point will be. Here's another example between just these 2 points, again, ignoring all the others. So there are, and you can do decision boundaries between all pairs of points, but we know that there should be kind of a way to generalize this per point. So not just the pairwise decision boundaries between pairs of points, but could we build the decision boundaries between all points? In essence, we can, and that's what's called a Voronoi mesh. So notice that now around each point there's a polygon, and that polygon defines the region around that point where that point is the closest. So if I have a new query point here, since it's within the kind of Voronoi region of this point right here, this query point would automatically be the nearest neighbor of this query point would be that point. If it was here, it would be this point. And there are kind of ways of building this algorithmically, and Voronoi meshes have several advantages. They're used very often in visualization. So for example, if these points were points on a map, for example, archaeologists use this a lot. And if those points are, let's say, settlements, and let's say a new settlement comes in, they can directly look on the map and see which new settlement it's closest to, etc. They're used for kind of 3D surface generation. If you have samples of points from the surface of a 3D object, you can build a so-called tessellation based on the Voronoi mesh. And the building of it is actually not that difficult. If you're interested, I suggest you go to Wikipedia and look at Fortune's algorithm, which is kind of a straightforward way of building Voronoi meshes. So finding the nexus points of the mesh and the equations of each of these lines. And while Fortune's algorithm does this by growing, kind of sweeping a line through the data set and essentially growing parabolas around points, an easier way to think about this is, let's say I tried to make a program that would make these Voronoi meshes. What I could do is, for each point at time 0, I'd have a little infinitesimal circle around each point, and so on and so forth. And let's say at time 2, I infinitesimally grow each circle. Right, now these two grow. And let's say I do that for the others as well. I'm just going to go on with these guys. And next time I grow these circles, notice that, for example, this circle and the circle on the other side actually touch. And the point where they touch is a point on the Voronoi mesh. And you can keep growing these circles, and you can actually see that this point, this line will kind of get generated from here. And notice that since there will be circles growing from this point, at one point they will collide and build this line, and so on and so forth. That's an intuitive way of figuring out how a Voronoi mesh is built. There's actually, if I'm not mistaken, a animation in Wikipedia that actually shows this really nice. If it's still there, I'll splice it into this video so you can see what I mean. So, when we're doing k-nearest neighbors classification, how do we decide what the class of a new point is going to be? Typically, it's pretty straightforward. Let's say we're using, in this case, three nearest neighbor classification. And obviously the new point we don't know the label of, but other points are already labeled because our data set contains the labels. And let's say in this case our labels are orange and cyan, I guess. Okay, so you find the 3 nearest neighbors, and what you do is you maximize the label for which most of the neighbors agree. So in this case, if it's just two classes, just orange and cyan, then you have to go and say, okay, now I have 2 cyan neighbors and 1 orange neighbor. So if I pick orange, it's only 1 agreement. If I pick cyan, it's two agreements. So cyan is the right class for this point. That only works though, and this is what we would call a majority vote. And notice that the majority vote only works if you have 2 classes. Let's say there's also a class of, say, red points around, right? And over here, for example, let's say, okay, let's put another red point over here. So now we're essentially doing 1, 2, 3, 4, 5, 6. That's not a good number. So let's also have orange. So let's put an orange point here as well. So now when I look at this, how many cyan points are there in the neighborhood? There is 1 and 2 of them, 2 orange points and 3 red points, which means no particular color has, or class in this case, has a majority, because the total is 7. The highest one is red, but it's only 3/7, so it's not the majority. It doesn't have more than 50%. So that's what brings us to what are called plurality votes. So this works for any number of classes, and what you're doing is you find the class with the highest number of members inside the neighborhood. So in this case, the correct classification would have been red, because although it doesn't have the majority, it has the highest number of representatives inside the neighborhood of our new point. So that's what the argument max is. You find the argument, in this case, argument being a label for this new point that maximizes the total agreements between that label you picked and all the other labels within the neighborhood. So within all points of the nearest neighborhoods, the k-nearest neighborhood of the new point, look at how many agree. And this function, by the way, is what's called the Kronecker delta. It's a very simple function. Basically says the Kronecker delta of any points, let's say any values a and b, would be, it's a piecewise function, so it's 1 if a is equal to b, and 0 if a is not equal to b. So it's just an if sentence, right? A mathematical if sentence. If y and yi are the same, this comes up 1, otherwise it comes up 0. So if you pick the right y, for example for red, there's the Kronecker delta will be 1 for 1, 2, 3 cases when y is red. It will be equal to 1, 2 cases when you pick y is orange, and it will be equal to 1, 2 cases when you pick cyan. So if you pick red, the total here, 3 ones would equal 3 on the total. So that would be the y that maximizes the vote. So that's the y that gives you the plurality vote. So that's what this says mathematically. One other consideration here is obviously you need to pick a k that's relatively prime to the number of classes. So it should not, your k essentially should not be a multiple of however many classes you have. So for example, here we have 3 classes with the red, the cyan, and the orange. And notice what would happen if, let's say, I had this case where you have one more orange, right? And one more cyan. Well, in this case, the blue will stand in for cyan. Now I have 3 of each. Because it's a neighborhood of 9 things and 3 classes, I might have a problem with trying to decide when each one comes up equal. There are still cases where this will be a problem, even in the original case where you don't have the cyan thing. If you're working with a neighborhood of, in this case, 8, so So 1, 2, 3, 4, 5, 6, 7, 8. Even then, there's 3 oranges and 3 red. Again, it's difficult to decide in this case, but at least if you take a k that's not divisible by the number of classes, you eliminate a whole class of problems trying to decide on the plurality. Obvious example, obvious kind of instance of this is when you have just 2 classes, you always want k to be an odd number. So that's why you typically see in KNN things like 1 nearest neighbor, 3 nearest neighbors, 5 nearest neighbor, 7 nearest neighbor, etc. Because essentially you're trying to avoid even numbers. Now, so far we looked at classification. Another kind of task you can do is regression. And now instead of voting, we do averaging. It's very straightforward. Let's say we take the 3 nearest neighborhood of this new query point, and the red number we don't know yet. That's what we're trying to find out. What's the value of this point for the target? And what we do is we take the 3 nearest neighbors, and now each one of their labels are not kind of classes like colors, etc., but they're actually values, continuous values. And a straightforward way is to take those n nearest neighbors, so k nearest neighbors, and take their values and take the average. In this case, 5.5 plus 6 plus 3.2, overall we'll get 4.7, and that's how we regress to the value of this new point and decide it's 4.9. So this is how you would apply k nearest neighbors to regression instead of classification. So one of the problems with k nearest neighbors is what's called the curse of dimensionality. I mean, we talked about the curse of dimensionality at length before, but KNN, k nearest neighbors, is particularly vulnerable to this because essentially what you're doing is you're looking at the distances between points. And this is all fun and roses when you're just working on 2 dimensions. But now remember our discussion about what happens to distances and similarities when you get to higher and higher dimensions. In a 20-dimensional, 30-dimensional, God forbid, 1,000-dimensional space, these distances stop making sense. That's the reason why KNN would be kind of particularly vulnerable to the curse of dimensionality because it lives on these distances. So you might be looking at distances as a particular potentially very sparse space. So what can you do? So we've seen some of the things we can do. You can actually take that high dimensional space and reduce it by looking at the distribution to a lower dimensional space like we did with PCA or kernel PCA. We haven't talked about it, but I'll put links in the course on explanations of these. But there are other dimensionality reduction methods like multidimensional scaling, special case of multidimensional scaling called isomap. I think we already talked about this. At least we talked about how it works. And t-SNE, so stochastic neighbor embedding. And these all will reduce a very high dimensional set into a meaningful low dimensional representation if they work, and that's some if. Or you can do feature selection. So you might know that, for example, in your 20-dimensional nearest neighbors, 15 of the dimensions aren't useful from the domain knowledge that you have, and just throw them out and just use the 5 dimensions that are left. And later on we'll look at things like gain-based feature selection, where you take different subsets of features and see how well your classifier does on your data set with the different configurations and try to optimize for the best subset. So here's the basic k nearest neighbor algorithm now, and it's a kind of an extension of the previous one nearest neighbor algorithm we saw. The only difference is, if you notice that this part is more or less the same as one nearest neighbor, and what you do is essentially you use that core, this for loop that's the minimum for loop from before, to build a set of nearest neighbors. So you start with an empty set called d prime. So that's going to be the set of your nearest neighbors. And while that set has less than k elements, so if you're looking for k nearest neighbors, k closest points to your new point, again, inside this while loop, it's the same as one nearest neighbor. You start without knowing what the nearest neighbor is. You equate the distance to 0, and then you start looking at the points inside your data set one by one. Here's an extra condition now. It should be a point that you haven't already put into your list of k nearest neighbors. Makes sense, because if I find the closest point, put it into d prime, and then start looking for another point, if I see the original point that I put in, that's going to be the closest, so I'll put it in again and then put it in again, and this will never end. Or actually what will happen is your d prime set will have 3 copies of the closest point. So you ignore points that you've already added to the set of nearest neighbors. And then the rest is the same. You look at the distance between points that you haven't added into the nearest neighbors yet and find the smallest one overall. And then you just add that smallest nearest neighbor along with its label to the set of to the set d prime at the end of this algorithm. You're left with a set that has exactly k elements, which are the k nearest neighbors and their labels. And then you can do your plurality voting or averaging, whether you're doing regression or classification, and so on and so forth. What's important in this algorithm is its complexity. If you've taken the data structures class, MIN720, you already know about big O notation. If you don't, it might be a good idea to look it up, but what we're trying to do is figure out how fast will this algorithm be if I know, depending on what k is and what n is. So what the size of this whole data set is. It turns out, if you just look at it by inspection, this outer loop while has to kind of iterate k times. So if you're looking for 3 nearest neighbors, this will iterate 3 times. This inner loop iterates n times for each one of those k, and within each iteration of the inner loop, you have a distance calculation. And now technically this distance calculation is of the order m, which is the dimensionality of these vectors. So if I have a 2-dimensional vector, I have to take the difference of these 2 vectors in 2 dimensions, square them up, and take the square root. If it's 3 dimensions, I have to take difference in the first dimension, the second dimension, third dimension, and then kind of square them up and take the square root. So however many dimensions you have on x, you have to do that many kind of squared differences squared, and then take the square root. So it depends on how high dimensional the data is. Obviously, this is for Euclidean distance. You might have distance metrics that don't get affected by the dimensionality, or you might have distance metrics that get more than linearly grow faster than linearly with dimension size. So in summary, we can basically say that at least naive k nearest neighbor is O of n times, so in the order of n, so linear in to n, but we're making some assumptions. Like we said in the previous slide, it's actually the number of k chosen times n times the dimensionality of the data set. But what happens mostly in practice is, although it takes O of m time to calculate each distance, usually number of dimensions is much smaller than the number of instances. So if it's, for example, just a 2-dimensional, 3-dimensional data set, you can just assume O of m is constant. Likewise, if you're doing just three nearest neighbors or something with 1,000,000 points, that 3 is not going to be that important. You can take it constant, and then you'd basically have O of n. Even that, then O of n might be too slow if you're trying to do fast classification. What's good is, again, if you've taken the data structures course, you can actually start with building a tree on all the points in your data set. Obviously, this is not going to be a binary tree, but what's called a k-dimensional tree, which is kind of like a 2-dimensional binary tree or 3-dimensional binary tree, however many dimensions your data set has. And what you're doing is, when you get a new query point, you traverse down the tree in log n time and find the closest point, which means finding the closest n points, closest k points, is essentially k log n. So that can speed things up a bit. So if you have a problem where you're trying to run k and n, but you have to kind of do it faster, you might want to look at KD trees. Another way to do it is kind of that will give you advantage might be a min heap. This helps when, especially when k is large, because instead of iterating for each of the k neighbors, what you can do is build a heap of the closest neighbors. Let's say you're looking for a 5 nearest neighbor thing. You build a heap that will have a maximum size of 5. So when you reach the size of 5 and then you have to add something more, you remove the farthest away. So actually what you're using is not a min heap, but rather a max heap instead of in the place of distance. So what you're doing is you will have this heap of 3, let's say 5 nearest neighbors. First thing goes in, the closest thing you find so far goes in, next thing goes in, and so on and so forth. And the 6th thing that you find, you check against the top of the heap. Remember that a heap always keeps its maximum member at the top, and the new point you find, if it's larger than the maximum distance, then you can throw out the maximum distance and put this in instead, and then the heap reorganizes. So when you're using a min heap, instead of being k of n, assuming you don't use m is very small, so being k of n, it becomes log k times n. Okay, so that's another speed up. What's even more interesting is parallelization. Now we live in the kind of age of multiple cores and cloud instances that can work in parallel, etc. And you might notice that the problem of k and n is actually embarrassingly parallel. So this for loop here is actually independent for kind of any xi. So you can, in parallel, calculate the distances for any new point and combine those, something like MapReduce or something of a merge sort type of thing. And actually, if you have billions and billions of instances that you want to find the closest neighbors of for a particular point, you can just parallelize that across cores, or even if you're working at a web scale, across machines. Usually though, what you do is you use a mixture of both this thing and the KD tree and parallelization. And those are all kind of ways you can speed up nearest neighbors. Slightly out of the scope of our course. What is in the scope of our course is pruning. So what can I do to the data set to kind of make it easier to find nearest neighbors in case when I'm doing classification. So now the question is, if I'm doing classification, do I need all the points, or can I get by with kind of a smaller version of my data set where then I would effectively decrease n, so I have to check the distances against smaller number of potential neighbors. So, but this is called pruning. So the first method you could do pruning is through editing. Let's take this example where we have two classes and the blue points in our data set are one class and the red ones are the other class. Notice that when you build the Voronoi mesh, there's a clear boundary here between these classes. So it's roughly this over here, right? And notice that on the border regions, there are points that are necessary to kind of, to distinguish between classes. But if I have a new point over here, I don't really need all of these points, because when you look at these kind of Voronoi regions of the border points, anything that's closer to the blue class than this point going this way has to pass through the Voronoi cell of one of the border points. So I can technically get rid of all of these points and all of those points. And notice I mean the smaller size ones. I've kind of enlarged the border points, so I can get rid of most of my points as long as I keep the border points. Because notice that whenever I have some random point in this space like this, it cannot be closer to any one of the red points without being closer to one of the border blue points. So the rest of the points are necessary, are unnecessary. And this can easily generalize to 3 or 4 classes, something like this. Then you take these border points as well. One other thing you can do in terms of pruning is, let me just clear up this mess a bit. Let me do it like this page. One other type of pruning we do is pruning of outliers, especially if k is small, like k is equal to 1. Notice that, as long as k is greater than 1, so you're looking at more than one neighbor to make a decision. So let's say as an outlier, the case is still the same, but this point just happened to be blue due to noise, some some outlier process, etc. Notice that when I use, for example, 3 nearest neighbor, even if I have a point here, a new point, only this one will be one nearest neighbor, the others will always be red. So this is alone and surrounded, which means it won't affect the outcome of the classification. The outcome of the classification in this region will again be red, doesn't matter whether this blue point is here. So you can actually If you have outlier points like this and you're using anything other than one nearest neighbor, you can actually get rid of this. So that's another way of pruning. So that's editing in terms of pruning. Another way of pruning is what are called prototypes. So prototyping. So instead of taking all the points in your KNN data set, you pick certain exemplars. So you try to pick these as kind of as a good sample as possible of the actual set. So they define the region occupied by the class they represent, and try to kind of so that the boundary is still more or less the same as the original boundary with all the points involved. And obviously there can be small differences, but sometimes the kind of gains in speed make the losses in accuracy worth it. So how do you find these prototypes? At this point, remember last time we talked about unsupervised methods in PCA, etc. One very common method that we haven't talked about, I'm assuming most of you already know this, but just to quickly go over it, is what is called k-means. So the k-means is a method of, in this case, actually finding those prototypes, finding those centers, and it is a clustering algorithm, clustering method, which does partitional clustering. So each point, when clustered, belongs to exactly one cluster. So you pick the number of clusters, and then what k-means does is it finds centroids for each one of those clusters. So if you can do it correctly, the centroids can actually act as prototypes. And each point in the original data set is assigned to the cluster with the closest centroid. So here, for example, if this is my centroid after k-means, all of these points that are closest to it are going to be represented by this point only. All of these points that are closest to it are going to be represented by this point. So this gives us exactly what we need. The algorithm is very simple for k-means. You start with k points, usually random points, as initial centroids, and then you assign all points to their closest centroid, whichever one it is, and then recompute the centroid of the cluster by taking the average of all the points assigned to that cluster. And you repeat this until the points don't change. So if we go through a quick example of this, let's say this is my original data, and these are my 3 random centroids. Initially, all the kind of the burgundy points are assigned to this centroid. All the green points are assigned to those the green centroid, and all of these blue points are assigned to this centroid over here. And notice that the shapes are slightly different. These are the true classes. So circles are one class, the diamonds are one class, and the squares are another class. So once I assign these points to each centroid, now let's look at what's going to happen. So since all of these green points are now closest to this point and are assigned to this point, the average of all of these points cannot be here. Think of it like a center of gravity. So it has to, the new centroid position has to move to somewhere like here. And likewise, this one has to move somewhere here. This may stay more or less the same at the first iteration. So the first iteration, after you're done, these guys have moved, and now you recalculate the closest points. So their regions have moved with them as well, and now the top centroid has more items from here. And obviously it has to be recomputed. Probably it'll shift this way. This might shift that way. This might shift that way. So that's iteration 3. And you keep doing this until the shifts stop. There is no difference in membership. And once you're done, k-means has found centroids for the 3 densest regions. And if these were kind of points for a K and N data set, you could just throw out all the points and just use the centroids, and any new point that you want to classify, if it's closer to this centroid, it's blue class. If it's closer to that centroid, it's green, and so on and so forth. Excuse me. So that's k-means. Like I said, the initial centroids, the initial position of these k centers is chosen randomly. And then once you do this, essentially k-means itself takes on the order of n times k times I times m iterations. The good thing is number of iterations is I, but it doesn't take too long. K-means a form of expectation maximization, and those kind of methods generally converge pretty quickly. You'd expect k-means to converge within a single-digit number of iterations. So most of the time, this can be taken as constant. M, again, is the number of attributes, and this comes in because you have to calculate distances between points, and the more high-dimensional they are, the more kind of time it takes to calculate distances between them. K is the number of clusters, again, because you have to do this for every cluster separately. And N obviously is the number of total points, because you have to calculate the number of the distance of each point to the centroid every time. So again, if M is rather small, I is assumed to be small. If the number of clusters is small, you're basically looking at O of N. So linear to the size of the data set. But once you do that notice that for classification, you only have to do k-means clustering on your data set only once. And to find these prototypes, once you found those prototypes and use those, any new query is just going to take time on the order of the total number of prototypes, which is much less. So you're basically taking the cost of doing k-means once just to speed up k nearest neighbors later on. The problem with k-means is if you choose the centroids poorly, so instead of the original centroids which were like this, let's say I chose these initial centroids, it can actually converge into a suboptimal solution. So since these centroids cannot go past each other by shifting, they'll be trapped in this cluster and kind of own two pieces of that cluster, where the third centroid will have to take the actual two clusters altogether. So it depends, the result you get with k-means will depend on how well you choose your initial centroids. And if you were using these prototypes for k nearest neighbors, notice that these two are different classes. You would have one prototype for two different classes, and if I have a query here, then it's closest to this point, but I don't know whether this point is a circle class prototype or a square class prototype, because it belongs to both, so that wouldn't work for prototyping. So what can you do to get the right centroids for prototyping? You can do multiple runs. That sometimes works, but probability is not on your side, especially if it's a high-dimensional data set. Then there's increasingly less probability that you will pick a good set of centroids, because the possible solution space kind of is much larger with higher dimensions. What if you can say essentially select more than k initial centroids, and then select among these initial centroids and select the most widely separated. So you use more than, you kind of start with more than the number of clusters you need, and then kind of take only the ones that are far apart away from each other, so that you know those aren't the ones that actually have kind of crashed into each other. And obviously crashing into each other is very obvious here because we're looking at this in a two-dimensional data set and we can actually plot it, but always keep in mind that you might be doing this on a 60-dimensional data set, so you don't actually know where the centroids are, or you can't visualize where the centroids are. And one other method is what's called bisecting k-means, which is a hybrid of normal k-means and hierarchical clustering. And it's generally not as susceptible to initialization issues. So the basic algorithm there is, in the middle, it's actually normal k-means. You're using basic k-means like we saw before, but you initialize first the list of clusters to contain the cluster containing all points. So you start with one big cluster, and then you select that and you run normal k-means. You limit the number of iterations, but usually this is not a problem. So you run normal k-means, and for, let's say, you run k-means with k is equal to 2. So you basically divide your initial large cluster into two small clusters. And within that, you pick the one with the lowest squared error, which is the lowest total distance of all of its points to its centroid, so that you pick the tightest cluster, in other words, and you put it into this list of clusters. And then you go back and do it again. You pick a cluster, you divide it in half, and keep the one that has kind of tightest collection of points, put it back in. You do this division until you get k clusters. So the idea here is like this. So if we start with this initial case, this is one cluster. If I just do k-means with two clusters, I get this large cluster and that large cluster, and I pick one to bisect. So for example, I'll pick this one and now put two centroids in the middle of that and recluster. So the original two clusters, this one stays. We don't touch that. We bisect the larger one. So now we're done in second iteration. Now we pick again. Let's say we pick, in this case, this one, and run two k-means with k of 2 on this one. It bisects again, and you keep doing this, and hopefully at the end, instead of doing 10 k-means with k10 and trying to figure out where the initial centroids should be, you start with just two centroids and keep doing this and start doing it by bisecting. And this tends to be less sensitive to the location of initial centroids. Okay, so I want to talk about the limitations of k-means, and obviously this is the nearest neighbors lecture, but the limitations of k-means actually map well onto the limitations of k nearest neighbors, because at this point you should have realized that they're using the same idea. The centroid, you can think of the centroid as the query point, and you're taking the nearest neighbors of that centroid to be that cluster, whereas in k nearest neighbors, you're taking the query point and trying to find the classes of the nearest neighbors to give that point a class. So it's basically the same dynamics. So these methods, in this case k-means, but also k nearest neighbors, would have problems with when there are clusters of different sizes, of different densities, and especially when clusters are not complex, so they're not non-globular shapes in whatever many dimensions you have. And also they would have problems when the data contains outliers. We'll see how we handle outliers with k nearest neighbors in a minute. So here's, for example, an example where you have a large cluster. So the different size clusters, this is a large cluster, and two smaller clusters. If you tend to run k-means on this, k-means would do the clustering like this. Okay. And likewise, if you do k nearest neighbors and, for example, pick this point, it's equally likely that it will be, say, blue versus red, but this red group is actually much larger, so one intuition would say that it should dominate, but even if it's right here, the point you're asking for, you might get blue. So it's the same problem. One thing to be careful about. So k-means tries to kind of build equal size clusters out of your data, unless it gets stuck in some local kind of centroid crunch. Likewise, if you have equal size clusters, so there's exactly the same number of points here as opposed to this cluster and that cluster, but one of them is much sparser, so its points are kind of spread across space. If you run k-means on this, you're likely to get this situation where, again, it will try to get the same number of points, but then one centroid will try to move to the outlying points and essentially only cover half of an actual cluster. The other half will be done by the second centroid, and this third centroid will have to handle two natural clusters all by itself. And obviously, since especially when we're using Euclidean distance, shapes that are not kind of convex or globular cause problems, because with that distance matrix, this point is as close to this point as that one is. So, but it's obviously from a different space view rather than Euclidean. These are very different clusters, but k-means will not be able to figure that out unless you use some kind of kernel or retransform the point somehow, or use some different distance metric. And this goes for k-means and knn as well. We've already talked about kernels, and you can use kernels for both nearest neighbor methods, and you can use k-means kernels for k-means as well. So several kind of modifications you can do for k nearest neighbors. One is weighted features. So let's say you have an instance with 5 dimensions, 5 different values for each example, and you know that some of the features are more important from the domain. Say, for example, you might say the position of the eyes on a fish doesn't make any difference for whether it's salmon or sea bass, etc. What you can do is build a weight matrix that has the weights of different features, more important features getting higher weights, and less important features getting lower weights. And instead of doing straight Euclidean distance, you can actually interject that weight inside the calculation. So for features that are kind of less critical, they affect the distance less, which means you're getting more accurate results, hopefully. We've actually seen an example of this in Mahalanobis distance. You can basically use Mahalanobis distance in KNN just by taking this weight matrix and putting the inverse covariance matrix like we did in Mahalanobis, and essentially Mahalanobis would then be an example of weighted features type of approach. The other thing you can do is distance weighting. So far, for example, when we're looking at the class of a new point, if we're doing 3 nearest neighbors, we take the 3 neighbors and each has exactly 1 vote. So if 2 of them agree, then the nearest neighbors works. But what if it's situations like this? You have 1 point that you want to know the class of, and there's 1 point here, 1 point maybe there, and the third point is again red, but it's all the way here, and there are no other points. So yes, these are the three nearest neighbors, but this one is much farther away from x with respect to the other two. Now, what do? If you use straight k nearest neighbor, you would decide that x is class red. However, if you use distance weighting, you might come up to the solution that I'm going to weight the vote of each point, each of the nearest neighbors, inversely proportional to their distance. So you can take, for example, each vote could be one over distance for each, and then you look at what is the maximum vote. In that case, for example, blue might actually be the higher, be the preference, and X might be blue. Likewise, if you're doing a regression, instead of just taking the average of the values of all points, you take the average weighted by the inverse of the distance, which is the same idea. So, one last discussion is, in k nearest neighbors, what does k affect? So if I have, what's the difference of doing 1 nearest neighbor versus 3 nearest neighbor versus 53 nearest neighbor? And the general thing is, 1 nearest neighbor potentially has high accuracy, but it's a much more complex model than others, and it will likely overfit. We'll talk more about overfitting when we get to model evaluation. When you have higher Ks, you have smoother regions and less likely to overfit, but now you might have bias and may actually underfit. You need to find a sweet spot, which is all about kind of model evaluation, which we will get to later. So just to see what I mean, let's take a look at these examples. So here are about 100 points, 50 of which are in class red, and the other 50 are in class green. And these points were sampled out of known distributions, which have a decision boundary shown by kind of this curve here, which is a weird decision boundary, but this is the theoretical truth, right? So these were sampled out of Gaussians that were arranged around this boundary. So if the perfect classifier would have the region under this curve as green and the region above this curve as red. So when you do 1 nearest neighbor, it gets pretty close. It can kind of find the little curvature of this region, etc. But notice that even when there's one outlier here, for example, green, this whole region becomes green, which is obviously an error. This part should have been red. So little pieces of noise will affect it when you have a smaller k. That's what we mean by it has high variance and it's likely to overfit, because it's basically not generalizing well, but memorizing these outliers is part of the thing. If you go to too high of a k, like let's say in this example k of 41, which means to label a class as, let's say, red, I want 41 of its closest neighbors to be red, or the majority of its 41 neighbors to be red. Notice that now all of this noise is gone. These guys cannot actually affect the result, because most of their any query point in this region, only 1 or 2, or at most this many of those neighbors would be green, but most of them would be red. So the general boundary is now much more solid, except now because the number is too big, we start getting bias and underfitting. We're actually missing this region, which should in the ground truth be green, but isn't because of this high k we have. Now you might say it's overgeneralizing now. The original case, the problem was it was making exceptions for very small noise points, and here it's essentially making no exceptions and overgeneralizing. So the sweet spot would be something like this, K23, where you don't get the noise points, but you do still get this region, or at least most of this region, defined as green. So that's how you would do with K. And again, like I said, we'll consider this more in model evaluation, but essentially it's the way to find the correct K in most cases is trial and error. So you try with different Ks with a probably held out test set and see how well your model does for different values of K. So, in conclusion, we talked about K nearest neighbors and kind of K means as a close relative, but mostly nearest neighbor methods. K nearest neighbors is a relatively simple classifier to set up, so you don't actually have to do training. You just dump all your training points into a database, a dataset, a KD tree, whatever, what have you, and inference is just looking up the nearest neighbors from that database. It's also very simple to use online, meaning you can build the model once and you don't have to kind of do offline or batch training every now and then. As long as you get new training examples, you can just append them to the database and they start getting used as part of the classification immediately. And it has very few hyperparameters. You only have to decide on what K is, which we just talked about. And the second thing you have to decide on is the distance measure. It doesn't have to be Euclidean. Most of the time it is Euclidean, but like we said, you can use any one of the Minkowski family. You can use a kernel. You can use kind of other distance measures, and it's not always obvious what would work best. The prediction, though, can be expensive for very large for very large data sets, although it's linear, so it's O of n, order of n. But what if n is several billion? Then you don't want to be scanning through several billion instances every time you want to classify a new point, which might be pretty frequent as well. The good thing is this is an embarrassingly parallel problem, so you can, whenever a new point comes in, you can just calculate distances on different nodes and then combine them and find the answer. We talked about pruning, so you can get rid of most of the points in your database as long as they're not on the boundary or they're outlier points. Or you can do something like prototyping if you can. So you can actually reduce the size of your data set effectively without changing what the classification would do. And you said you can also use faster data structures, like, for example, instead of if K is large, instead of keeping a list of the K closest members, keeping a heap of the K closest members, or instead of using a linear scan over all the data set every time you want to find the distances between a point and a new point in the set, you might keep something like a tree data structure, in this case what we call a K-dimensional tree, which would make that search the order of log n. Probably the most critical vulnerability KNN has is its susceptibility to the curse of dimensionality. Like we said, since the whole thing is built on kind of the points within the neighborhood of a query point, so when you have a new point, you look at its neighborhood and try to find labels there and assign those labels to your point. When you go very high dimensional, those neighborhoods don't make sense anymore. There might not be anybody in your neighborhood. Or you might just have to grow your neighborhood to ridiculous sizes just to get 3 neighbors, which makes predictions very difficult with very highly dimensional data sets. So what you can do there is you can first run it through something like PCA or TSNE or kind of feature selection to reduce dimensionality prior, or you can build in that dimensionality reduction by using something like weighted features and a kernel to only actually combine features that are important into your distance calculation, effectively reducing your dimensions. So you can do it as a separate step, or if you can design a kernel that does that while evaluating distances, you can just plug it in directly into KNN. So that's all for today. I'll try to do a practice session on nearest neighbors soon.